Section 4.4 in college algebra is referring to logarithmic models. So remember, in the beginning of chapter 4, we talked about exponential functions and then exponential models. And now here we're talking about logarithmic functions in the last section, and now logarithmic models. So decimal level is a very common use for a logarithmic model. And the formula is 10 times the logarithm of, and I always forget what these variables stand for, but I believe I is the intensity of whatever the sound is, and then I sub naught is the threshold of hearing, I believe. So there's a chart on page 358 of your book, and we're looking at number 1 on page 363. So number 1 says we want to find the decibel level of the threshold of hearing, which is 1 times 10 to the negative 12 watts per square meter. So, it's a little silly because the threshold of hearing is also the I sub naught, the intensity of the threshold of hearing in the denominator. But when I use the formula, let's just go ahead and plug it into the formula. 10 times the logarithm of, you can do 1 times 10 to the negative 12th if you want, or you can just call it 10 to the negative 12th. And then over 10 to the negative 12th. And of course, 10 to the negative 12th over itself is really just a 1. So what you have is 10 times the log of 1, which is 0, I believe. And that kind of makes sense. There are 0 decibels if you're just at the threshold of hearing, because it will not make any sort of sound for you. Part B says the threshold of pain is 1 watt per square meter. So in the formula, it's a 1 over 10 to the negative 12th. The denominator is always the threshold of hearing, which is, you could say 1 times 10 to the negative 12th, or again, just 10 to the negative 12th. So for this, I'm going to type it in my calculator. Log of, I get 120 decibels. Then, example, let's see, number 5 on page 363 is referring to the Richter scale. And remember, the Richter scale is what measures the intensity of an earthquake. They call that the magnitude. So the magnitude of an earthquake is 2/3 times the logarithm of, let me look up what these variables stand for. E is the energy released from the earthquake, and E sub naught is the energy released by a very small reference earthquake, which they standardize E sub naught to be the constant 10 to the 4.4 power in joules. If you are curious what the measurement is, the unit of measurement, it's in joules. That's how they measure their energy. So example 5 on that page says we've got a strongest recorded earthquake was in Colombia in 1906. Its energy release was 1.99 times 10 to the 17th power. So that means the E in the numerator of the logarithm is, I just read the wrong thing, 1.99 times 10 to the 17th power. So on my calculator, using my formula, 2/3 times the logarithm of 1.99 times 10 to the 17th over 10 to the 4.4 power. And when you type this in the calculator, I want to make sure, in your calculator you need to make sure, well, you don't actually need parentheses here, but some people like to get in the habit in their science class of grouping numerators and denominators, but just carefully type this. 2/3 times the logarithm. (1.99 times 10 to the 17th divided by 10 to the 4.4, and I get a magnitude of 8.6, and I don't think, it just says compute to 1 decimal place, so that's what we want. The magnitude of this earthquake is 8.6. Okay, another logarithmic model. I believe this one is a rocket launch, but let me double check that. This is rocket flight. It's C times the natural log of, and then W sub T stands for the takeoff weight And then W sub B is the burnout weight. And they're referring to a space shuttle launch, I'm guessing. I know little to nothing about this, so let's keep reading. C is represented, let's see, exhaust velocity. And then the V that they're trying to solve for is the velocity of the rocket at burnout. So number 9 on page 363, it's actually on page 364, is saying that the C for this rocket launch is 2.57, and then natural log, and they actually give you the ratio of W sub T over W sub B, and that ratio is 19.8, and that was given to us in the problem. So we would calculate this to 2 decimal places, it says, so just carefully type. And you got 7.7. And if I look at the, let's see, kilometers per second is our label. I'm just going off the label that was in the other part of the question, the other velocity. Okay, example 4 is actually example 11 on page, again, 364. And this is a great use of a logarithm. In chemistry, when you're trying to find the pH of a substance, it's negative logarithm of the, and I might get this wrong, I think it's the hydronium ion concentration. So these equations mean the same thing. Visit your chemistry teacher for a more thorough explanation, but for example 11, it says find the pH of seawater, which has a concentration of 4.63 times 10 to the negative 9. So we're going to type negative and then the common logarithm of 4.63 times 10 to the negative 9th power. And again, just on the calculator, negative is a negative coefficient, not a subtraction sign. And so negative log 4.63. And it's seawater, so think about the answer that you're getting here. Remember on the pH scale, I believe it's 0 to 14, with 7 being neutral. This one came out to an 8.3 pH, which is towards the basic end of the scale, I believe. I always get those wrong. Part B, vinegar is 9.32 times 10 to the negative 4th. So on our calculator, negative logarithm of 9.32 times 10 to the negative 4th. Yep. And vinegar is actually called acetic acid because it is indeed an acid. His pH came out to 3.03 on my calculator, so I think they want 2 decimal places, or what did they want? Oh, 1 decimal place. 3.0 is our pH, which indicates that it is an acid. It's not a really super strong acid, but it is an acid. I guess that's it. Pretty short lesson on 4.4.